Of what?
How we're managing that's Dot, Melissa, Shannon, and Bobby are all sending out emails.
They're saying the same thing?
Oh no, they're all the bosses using different.
Let's see here.
Hey Dad,
Yep.
do you have a microphone on here? I can't hear anybody. It's not. I'm connected, I just can't hear anybody.
Should be working just fine.
I can't figure it out.
Oh, me neither. I think that she must be muted. Oh no, you didn't join audio.
Oh, I didn't?
Yeah, we can hear you now. I can hear you.
All right. Hey, is anybody here with us yet? Looks like we got some people here. All right. We got Maddie, we got Angel. Nerea will not be joining us today, so I'm recording. Oh, there's Rusty. How's everybody? Okay, we're going to start today by completing our videos viewing. So if you have any questions, make sure that you speak up. I will stop the video from time to time to discuss some things. And then when we're finished watching the video, we will go through some of the stuff that's in the homework and in the book for this chapter, and then we'll be done with this chapter. Any questions before we get started? All right. There are no questions. Let's go ahead and get going with the end of A is for Adam.
And plutonium will fission and chain reaction. Thus, this type of reactor itself becomes a source of atomic fuel. But nuclear reactors also make possible other very important uses of the energy.
Okay, so actually, before I get too far into this, just so you know, my daughter is actually listening in on this, and she had a question last time that I think I should relay to the rest of you. In this process of the nuclear reactor, um, they talk about using uranium, which U-235 goes through a fission process and turns U-238 into plutonium, which can also go through a fission process. And my daughter said, so why don't they just do that with the old fuel? When the fuel gets bad, why don't they just put it back in and make it into plutonium again, and then you can use it again? And the answer to that question is, the short answer to that question is that you can do that. Um, and so nuclear fuel is actually completely recyclable, can be used over and over and over and over again, ad nauseum, really. The problem with it is that when you're making plutonium, U-235, which is used to make the plutonium, is very rare and very difficult to find and separate. Whereas if you can make plutonium, all of a sudden you can make a lot of a material that can be used in nuclear weapons. And so it's very, the production of plutonium is very regulated. It's regulated throughout the world. It's regulated in the United States in particular. You cannot make plutonium. You cannot have this kind of a reactor that makes plutonium if you're just some random energy company. You have to be a government to make this, and they've actually prohibited some governments from making it by sanction, particularly governments that are known to be hostile governments that have tried to take over other countries. So, for example, Iran and North Korea have both been trying to start up their own kind of plutonium making plants, and also Iraq tried that 20 some odd years ago, and that's one of the reasons that um, there have been so many wars over there. Probably the main reason is that they just have oil, and there's a lot of money in oil. But anyway, the point is that this is a great way to perpetually make energy. But as long as we have people with imperial ambitions and dictatorial dispositions in this world, you can't just let this technology be freely used everywhere. You have to regulate who uses it and who doesn't, to maintain peace and to maintain some sense of order. And that's something that if I said that in a class in, say, Europe, if I was teaching in Europe right now, or some other country like New Zealand, because New Zealand is highly anti-nuclear, I would get berated for that, because a lot of people believe that Americans are the worst example of this, because we're the ones that developed the first nuclear bombs, and we have prevented many, many other countries from doing so. But I put it to them that that is not the case, that we are not arrogant in our assumption that we should be the only ones to have this ability. We are, yes, the people that used these bombs to end World War II, and many people in the world say, well, you didn't have to use that. That's a very politically charged thing. You didn't have to do that. Japan was losing anyway. But the thing that most people never understood about Japan, that Americans did understand, because we had many Japanese people in our country, especially in Hawaii and California. The thing that we understood about Japanese people and the Japanese culture that most people in the world did not understand is they had, and they still do, it's very much part of their culture, this idea that if they didn't achieve their goals, they would die trying. They were willing to kill their entire country, essentially, to try to achieve this goal, even if they knew it was impossible. And the choice to drop those bombs was as much to save Japan from extinction as it was to end the war. And to save also other lives, American lives in particular, in the Pacific. And so the political ramifications of all of this are very deep and very, well, deeply felt and deeply. There's a lot of opinions about them throughout the world. While we are the only um, country in the world who's ever used nuclear weapons, we are also the only country in the world that has essentially stayed our hand in many of these things. We have gone all over the world and had the ability to take over many countries over the past 100 years, but we haven't done so. And many people say, well, what about Puerto Rico? What about the Philippines? What about these other places that the United States kind of interjected themselves into? Well, every single one of those places that we've interjected ourselves into, we have offered to back out. And the people that lived there voted and said, don't back out. That includes the Mariana Islands. That includes the Philippines did vote to have us out, and we left. It took us a while to get out, but we did leave. Puerto Rico has voted time and time again, and they want to stay U.S. protectorate. So this is not, the science of this is one thing, and it's important to keep the world safe from people making plutonium all the time. But the politics of it are another very important thing. It's always important to realize that politics and science often go hand in hand, and this is definitely one of those cases. So there are countries in the world that have power plants that are completely controlled by their governments, and they are recycling their materials. They're recycling their fuel rods so that they can use them indefinitely. That includes Japan. It includes, and Japan, of which, by the way, we did bomb Japan and we did occupy Japan for a short time after World War II, but Japan is completely independent of the United States at this point. I think we still do have one military base, one Air Force base, I think, in Japan. But besides that, I mean, Japan is a completely autonomous country, has no obligations towards us except that we rebuilt their economy, and they have treated us very kindly ever since. The point is that we dropped bombs on them, and then we rebuilt their economy. We actually gave them nuclear power technology because they have very few resources to make energy. So I think that what America has done with nuclear power has proven that we are good custodians of this science and good custodians of this power. All over Europe, the nuclear power plants are owned by the governments, not by private entities, and so they're also recycling their nuclear fuel, their rods, and that's totally fine. The reason we don't do it here is politics. In the 70s, we decided to not allow that to be the case, and so none of our commercial reactors, which all of our nuclear reactors that create power are all owned by private companies, and so they are not allowed to recycle their fuel because they're private companies. We do have many reactors that are owned by the government that are not used for making power. They're used specifically for weapons research and pure scientific research, and they can recycle their fuel using what's called a breeder reactor, which essentially reinvigorates the fuel and makes it usable again in a nuclear reactor. So anyway, just a question that came up after class last week that I wanted to share the answer with you.
Then to plutonium. And plutonium will fission and chain reaction. Thus, this type of reactor itself becomes a source of atomic fuel. But nuclear reactors also make possible other very important uses of the energy in the atom. Remember, the chain reaction process in a reactor produces a tremendous heat, which scientists have learned to control and safely put such fission reactions to work. In a conventional boiler, coal, oil, or gas provide the heat needed. In a nuclear plant, the heat of fission replaces the coal, oil, or gas, boiling the water.
This is kind of an interesting image because it shows the nuclear reactor kind of underneath the water in the boiler, which in many cases is actually true. Uh, they often do put the nuclear reactor underwater, and then they transfer the heat out of the nuclear reactor. Doesn't mean that the nuclear reactor has water inside of it. It just means there's water surrounding it. And one of the reasons that's a good thing is that water is a very good absorber of neutron radiation, or free high energy neutrons. And free high energy neutrons are one of the major dangerous uh, radiation forms that come out of a nuclear reactor. Neutrons are particularly dangerous because they are very massive. They can accelerate very quickly. And when you have something very massive and moving very quickly, it'll penetrate things like your skin and your bones and things like this. And so when those particles come in contact with humans, or even if they come in contact with metal, they just start taking it apart. So one of the things that you have to do if you don't want to have to replace everything in your reactor all the time is you need to do something about neutron radiation. So surrounding with water is a very good idea. In fact, the laboratory where my father worked did a lot of nuclear research. It still does, in fact. And they actually had buildings 4, 5, 6 stories tall that were just big tanks of water. They looked like normal buildings. They even put fake windows on them and doors just to make them look nicer than just big brick edifices, or big, block concrete edifices. But really, they were just filled with water, and the whole purpose of them was to prevent neutron radiation from getting into the area surrounding the laboratory, because it's in a reasonably populated area in near San Francisco. So it's a really cheap way to shield from neutron radiation. The other thing that's great about water is that not only does it shield from neutron radiation, it also can stop the reaction for the same reason, and it can also cool the reaction. So if you have if you have an overload in a reactor, which is often called a meltdown, what happens is that you get too much heat in the reactor, and it starts to melt the fuel rods. It actually starts to melt the uranium or the plutonium inside the reactor, and then that uranium and plutonium will melt through everything that it's around, the casings, the graphite blocks, everything. It gets so hot it will melt everything, and it'll just form a big puddle down here at the bottom of the reactor. Well, the problem with that is that if you get enough uranium 235 or enough plutonium puddled in a small place, it actually will become a bomb. It will actually explode as a nuclear bomb. And so you don't want that to happen. Anytime a nuclear reactor starts to go on a runaway reaction, starts to get a little too hot, what they'll do one of two things. They'll either shove in a bunch of control rods. They can actually remove the fuel rods as well, but the best thing to do is to shove in control rods, which are like fuel rods, except they have no fuel in them. They're just filled with things that block neutron radiation, so they prevent the chain reactions from accelerating. And if that doesn't work, what they'll do is just flood it with water. They'll just open up there are some valves on the outside of this thing, some kind of gates, and they just flood the whole reactor with water. Now that's kind of a last ditch effort to save these things usually, because that creates some of its own problems, can destroy the inner workings of the reactor. But it's a quick safety precaution that you can use to stop a runaway reactor. So
which produces steam to turn the turbine, which is connected to a generator. When you realize a pound of nuclear fuel can produce as much heat as 2.5 million pounds of coal, the savings and convenience are easily recognized. Today, the most important use of heat from nuclear fission is for the production of electric power. Large nuclear power stations like Dresden near Chicago, operating since 1959 and providing enough electricity to meet the daily needs of over 250,000 people. Nuclear power plants like Big Rock Point in northern Michigan, Yankee in western Massachusetts, Humboldt Bay in California, 9 Mile Point in New York, plants overseas in Italy, in Germany, Japan, in India, and many others now under design and construction. Nuclear power stations like those symbolize the benefits of safe, clean, economical electric power to people all over the world. As reserves of coal, oil, and gas decrease, nuclear energy provides an increasing portion of mankind's growing need for energy. Steam produced by nuclear reactors also propels submarines and ships months without refueling. Scientists and engineers today are perfecting ways of using nuclear fuel for power supply in space vehicles and eventually for propulsion. Other valuable byproducts of the nation's reactor, aside from heat, are radiation sources and tagged atoms and radioactive isotopes. Research has revealed that many elements which are not naturally radioactive become so when placed in a nuclear reactor, and radiation from these isotopes, measured by devices such as the Geiger counter, aids the cause of science and serves mankind more and more in many different fields. In agriculture, radiation is now used to preserve food, to eradicate pests, and to test such things as the effect of fertilizers on plant growth and the proper timing for their application, helping to assure bigger and better yields from tomorrow's farms. In industry, radiation has found literally hundreds of new uses. For example, this atomic thickness control of sheet aluminum, saving hundreds of man-hours of labor and assuring accuracy never before possible. In the fields of medicine and biochemistry, radiation is performing near miracles. The radioisotope cobalt-60 is used to treat cancer. With radioactive sodium, doctors are learning more about heart disease and circulatory disturbances. Radioactive phosphorus has been used to locate tumors in the brain and greatly simplify operations for their removal. Iodine-131 finds one of many uses in revealing conditions of the thyroid, and there are many others. New ways of using radiation are being discovered constantly through the tireless work of modern pioneers in such fields as chemistry, metallurgy, medicine, and biology. Truly the superpower which man first released over 2 decades ago from within the atom's heart is today man's faithful servant. He is a defender, helping maintain peace, an engineer.
So the rest is
providing
just propaganda. We can skip that, I suppose. But I've always, since I first watched this video, I've always thought it was a great educational tool. So let's go to, actually need to go back to where I was and go to our textbook. Here we go. Let's go to the chapter and see what kind of things we can add to that video from the chapter. It really does do a good job of covering a lot of good material. So let's see where else we need to go here. Here they have a nice image of the brain. So in this one, they just talked about this in the video. So this is using technetium-99, which is one of these radioactive isotopes that's made by putting it inside of a nuclear reactor. And oftentimes with these things, what they're doing is they're actually you drink it, or they inject it into you, or sometimes you breathe something. And when you do that, it gets into your body in such a way that it's producing radiation. Now, this is not a type of radiation that's doing any real damage to your body, but it is radiation that is going to come out of your body so that it can be detected. There are 3 kinds of radiation that are kind of your normal, well, I suppose 4 that are kind of normal radiation. There's the alpha radiation, which is particles, helium nucleus particles, 2 protons, 2 neutrons. And we talked about that one earlier. Those were some of the first ones detected. They're quite massive. They're positively charged so that they're easy to see, to detect. And then there's also beta radiation, which is an electron which can be ejected. And believe it or not, the electron is ejected from the nucleus, even though there are no electrons in the nucleus. And what happens is an electron is born in the nucleus, and so that's a little bit different. We'll learn about that in a minute. And then the final one, which is the final two, there's neutron radiation, which we just talked about, these high energy neutrons that are kicking around. But then there's gamma radiation, which is light. It's essentially high energy X-rays that come out. And these are the kinds of things that you're seeing when you're using technetium-99 to detect things inside the brain. So the technetium gets into the different parts of the brain and it radiates outward. And as it radiates outward, it creates an image of the things that it travels through, the brain in particular. So, and different materials are used in different parts of the body because they go to different parts of the body. They're used in different parts of the body, or they get absorbed by different parts of the body so that you can see what's going on there. So here we got to talk about half-life here eventually, fission, fusion. Okay, we got a few things to discuss here. So you have the elemental symbols to start off with. So here we start with a few of them: copper, gold, iron, lead, mercury, potassium. All of those are considered metals. And then we have more here, aluminum. So aluminum is a metal. Argon is not. Argon is what we call a noble gas. We have gold, which of course is a metal. And then there's some other things in here that are neither metals nor gases. For example, carbon is kind of in between metals and gases. It's not really either. Calcium is definitely a metal, but let's see if I can find a different one here. Silicon is kind of in between metals and non-metals. We have things that are definite non-metals, things like, let's see here, what do we have? Well, carbon is a non-metal, but it's kind of in between the metals and non-metals. Fluorine is a non-metal. It's a gas that is highly reactive. Oxygen is a non-metal. Nitrogen is a non-metal. Neon is a non-metal. Iodine is a non-metal. Hydrogen, helium are both non-metals. So there's the table of the periodic table of the elements essentially has three different kinds of things in it. It has the metals, and they're all very much like the metals that we're used to seeing, like aluminum and iron, where they're usually solid. There's one that is not. Mercury is not solid at normal conditions, but it's still a metal. It's liquid. But they're usually, they conduct heat well usually. They usually conduct electricity pretty well. They're usually shiny-ish when they're not, as long as they haven't oxidized. You know how iron can rust, for example, but rust is not pure iron, so it's not considered a metal. It's a combination of metal and iron and oxygen. So metals, there's metals, and most of the periodic table is made of metals. Uranium and plutonium, for example, are metals. But then on the other side of the table, and most of the metals are on the left side of the table, which we'll show you in a second. In fact, let's just bring that up really quick. Let's see here. I have this periodic table in my classroom. You may have seen it. Where did it go? That is, there it is. So this is the periodic table that I actually have in my classroom. Oh, it's not very good. Can't see that very well. I need to zoom in on this a little bit better. There we go. So this shows you all of the metals. These are actual samples of these metals, pictures of these samples, and you can see that they're all very metallic looking, kind of shiny, definitely looking solid for the most part. The one that is the liquid at kind of normal temperatures is the mercury, which is, where is mercury? I can't see it here. I can never remember where mercury is, but mercury is not, oh, here it is. There's the mercury. So mercury is not a solid at room temperature and normal pressures. It's a liquid. But all the rest of these metals are very metallic. There's just a bunch of them, lots of them out here. Some of them don't look quite as metallic as others, like francium looks a little more like a rock maybe. Calcium looks a little more like marble, but these are definitely metals. They have all the properties of metals. But then once you start to get over here, you get to things like this. Like it kind of looks shiny, but it's not like a normal metal. It kind of looks crystally. That's called bismuth. Antimony almost looks like glass. It starts to look very much like it has shards to it. Germanium looks like kind of glass kind of thing. Silicon kind of looks metallic, but if you actually saw it in real life, it actually looks much more like glass. So does boron. Definitely carbon in its solid form is diamond or graphite. It definitely does not look metal. Um, these things over here that are supposedly metals that look kind of like metals do not at all behave like metals really, and they definitely don't really seem to look like metals. Here's an obvious one here, astatine. Astatine is very unmetallic looking. Selenium. Sulfur looks more like yellow chalk and stinks. Uh, that's what makes volcanoes and hot springs stink, is sulfur. In fact, that's actually why garlic and onions stink also. Garlic and onions are plants that are designed to absorb sulfur from the soil, and that's why garlic and onions smell and taste the way they do. So you have all these things which are not so metallic, and they don't have metallic behaviors. They don't conduct electricity like metals do. They have a very different way of doing that, very interesting properties as far as that's concerned. And then over here you have all these things that are gases and liquids, like radon is a gas, iodine is a liquid, bromine is a liquid, chlorine is a gas. Bromine is technically a gas also, actually, but it can be made a liquid pretty easily. Oxygen is a gas, nitrogen is a gas, fluorine is a gas, and then you have all these down here, which are all gases, all these here, and these things are certainly not metals at all, but most of it is. Most of this stuff over here is all metallic kind of stuff, and just these few that are kind of different over in this corner. And then you have all the symbols for them. Oops. There we go. In the periodic table, you have different numbers in each one of the boxes for each one of the elements. One of them is the atomic number, which tells you how many protons the atom has. Excuse me. And if you go back to the periodic table, it starts up here with hydrogen, which has 1 proton. So there's the atomic number 1. Right underneath that number is what's called the atomic weight. And for hydrogen, it's 1.000 something. And that's essentially its weight in proton number, you could think. So hydrogen just has, for the most part, hydrogen out there in the universe just has 1 proton and an electron kicking around. And so the 0.000 something is the mass of the electron compared to the mass of the proton. Oh, here it is. They actually show it right there. The atomic weight 1.008. So that 0.008 is the mass of the electron out there, where the 1 is the mass of the proton. Now, in what units is that? Well, that's not in any units, that's in proton masses, you could think of it as, right? Whereas helium actually has it has an atomic number of 2, you see, and then the atomic weight is 4.002. That's because most helium atoms have 2 neutrons as well as 2 protons. And neutrons have about the same mass as protons, just a little bit more, but not much. And so instead of having that atomic weight of 2 for the 2 protons, it has an atomic weight of 4 to add on to include those two neutrons that are there. And then you have lithium with 3 and beryllium at 4 and so on and so forth. You get down here to some of the ones that we know a little bit more, like carbon. It has 6 protons. Nitrogen has 7. Oxygen has 8, right? Go to copper with 29 protons. And lots of, but I mean, you see the atomic weight here, with 29 protons, it has an atomic weight of 63. Has more than double the number of neutrons, obviously. You can essentially, you can calculate it, essentially take that 63 and subtract off 29, and you realize that there are 34 neutrons in there. And you get up to gold, and it has the atomic number, or the atomic number of 79, but an atomic weight of 196. So way more. This almost has 1.5 neutrons for every proton. And that actually happens quite a bit as you get up further and further in the periodic table. For example, if we go down here to uranium, 92, uranium has the atomic number of 92, so it has 92 protons, but then it has 238 is the standard, right, number for the atomic weight. That's kind of the average. So that's almost 150 neutrons in it. 146, 148, whatever it is, 146. Has a lot of neutrons in it for its atomic weight. There's one that you maybe have heard before, neodymium. Neodymium is a what we call a rare earth metal, and it actually is what we use to make very strong magnets these days. So anyway, interesting things about the periodic table. The major parts of the atom, constituents of the atom, are put into this table here with their masses and their charges and their kind of locations, electron, proton, neutron. We've talked about those. You can see here that this, the electron has a charge. It's a negative charge. Proton has a charge. It's a positive charge. Same exact amount of charge, positive and negative. Neutron has 0 charge, right? And you can see that the masses of the proton and neutron are very close to each other, whereas the mass of the electron is much smaller, 10,000 times smaller, well, about 1,000 times smaller. They talk about Rutherford's experiment again, which we've already discussed. Mass number, neutron number. So here's something that they'll ask you in your homework: to calculate the neutron number from the mass number and from the atomic number. So the atomic number is the number of protons. They're using different words for these, and that's not uncommon. Here it's mass number is the atomic mass, and atomic number is the proton number there. So atomic number, we said that, we used that same phrase. And if you want to know the neutron number, then you just take the difference between these two. So the bigger one is going to be the mass number, the smaller one's the atomic number. Take the difference, and then that's that whole number that's left over. If you round to the down to the whole number, you will get the number of neutrons, or the neutron number, just like we did recently. And that's here, they're showing that right here. Okay. Here they talk about the nuclear strong force, which we've talked about. That's that binding force, that cosmic glue we talked about in the video that comes from the neutrons for some reason. And that's what holds the protons together. Otherwise, the protons would fly apart from the electric repulsion. this is something we didn't talk about, which is half-life. So with radioactivity, the radioactivity comes out of the nucleus, and it comes out of the nucleus because of these kind of random rearrangements that the nucleus goes through to make itself more stable, or to make itself to give itself lower energy, and so it releases energy in the process. But it is a random kind of occurrence. It's not something that is governed by any process that we know of, and it behaves completely randomly. So the first one, the alpha decay, this is what happens. You have, in this particular case, you have thorium. Thorium is a radioactive element. And it's kind of interesting. Thorium has been well known as a dangerous element for hundreds of years. It was used as a poison for a long time, a long-term acting poison, where if you gave people thorium in small amounts, in their food or something, it eventually would make them very sick or kill them. But they didn't know why. They just thought, it's just poisonous. But one of the reasons it's poisonous is because it's radioactive. And so thorium will decay into radium by alpha decay. And what does alpha decay mean? Alpha means that it kicks out 2 protons and 2 neutrons out of its nucleus. In other words, a helium, what we call a helium nucleus, right? And so this is I guess a chemical. This is the chemical way of showing this. But this is sometimes called a decay equation, or a reaction equation. So in chemistry, they call it a reaction equation. We call it a decay equation, because there's nothing really reacting; it just kind of happens. The thorium just becomes radium with the alpha particle. So this is the symbol for the alpha particle, since it is a helium nucleus. And like I said, this does happen. This does happen randomly, and so it behaves statistical laws. Another thing about this equation is that if you go across the top with these numbers, 232, 228, and 4, these two over here add together to equal this one on the top, and these two on the bottom add together to equal this one on the bottom, and that is always the case. You can't just lose any of those particles. Those particles have to be conserved. So here they have you write an equation for uranium undergoing alpha decay. So uranium-238, when it undergoes alpha decay, what happens to it? Well, you lose 4 particles from the 238, and you lose 2 particles from the 92. So it becomes something with a 90 in it. So you got to go look at the periodic table and look for the thing that has 90 in it, right? So we go down here to uranium, which is right here. This is 92, and you go down the table 2 spots to thorium, where that has 90. So you would put thorium in here, TH. That's what they do. Then beta decay. Beta decay is when you lose when an electron gets kicked out of the nucleus. And what happens with beta decay is a neutron actually goes through a decay process where it becomes a proton. So it decays into a proton, and then an electron is ejected. And a lot of students and even scientists, in fact, want to say that means a neutron is made up of a proton and an electron, but that is absolutely not true at all. There is no evidence that suggests that an electron and a neutron put together, an electron and a proton put together makes a neutron, or a neutron is made up of a proton and electron. It's much more complex than that, and much more mysterious than that as well. So you just can't make that assumption. There's just no evidence to support it. However, this certainly does happen. Carbon can become nitrogen by undergoing this thing that we call beta decay, where a neutron decays into a proton. So this number 6 in the carbon actually becomes 7 in the nitrogen. The 14 stays the same, just because one of the neutrons is now a proton. The total number actually up here stays the same. And the beta decay is symbolized by the E for electron, and they put a -1 down here to show that this neutron has this, sorry, the proton over here decayed, sorry, the neutron over, one of the neutrons over here decayed into a proton. So that 7 plus a -1, it still equals 6. It's just to maintain that, that conservation of particles there. And like I said, don't don't worry about it too much. The details, they are quite complicated, but suffice it to say that it definitely happens, and it doesn't happen the way that you might think. It's a bit complicated and crazy. The gamma decay, which we talked about, is where radiation comes out in the form of light. Well, in that case, it's just pure energy coming out. There's no matter coming out. And there's no matter conversion of any kind. There's no decay of a particle into another type of particle. It's just some energy is released. And so lead-204 will just become lead-204. It hasn't changed at all, except that maybe something inside of the nucleus changed in such a way that it has less energy now. And so it releases that excess energy. We don't really know all the details about how it might change. It's much too small to really see, detect in any way so far, but we certainly know that it happens. So those are 3 equations for 3 types of decay. They actually talk about 5 types of decay, a positron decay. And in a positron decay, a neutron actually becomes a proton. It decays into a proton and releases what's called a positron. So it's like the opposite of neutron decay. And then here we have neutron radiation, where a neutron is actually kicked out of the nucleus, in which case the nucleus just loses one of its neutrons. So here's an example of positron decay, where you start off with, let's see, F is fluorine, right? Can't remember. Fluorine F, yes, fluorine is F. So you start off with fluorine 17, and it becomes oxygen 17 through this positron decay, where one of its protons actually is going to now decay into a neutron, and it has one less proton now instead of one more proton. And then it emits what's called a positron. A positron is a type of particle that is just like an electron, except it's positively charged, and they're very rare. This is called antimatter or antiparticle. And the positrons are very rare, very, very rare, so rare that to observe them, you actually have to make them. They're not just kicking around out there in the universe, really. So they don't have a very long lifetime either. They usually end up combining with another electron. And when they combine with an electron, they actually disappear into non-existence. They go through a process that we call annihilation. So become pure energy. Again, an Einstein thing. So anyway, as we go through all these different transitions, as things decay, we end up with these, what we call, these are called decay paths or decay series. Here's uranium-238 going through alpha decay, loses 2 protons. And you can see here we have the mass number on the y-axis, and we have the proton number on the x-axis. So if you lose 2 protons, you go down on the x-axis. If you lose 2 neutrons, you go down on the y-axis. And then if you go through beta decay, you actually gain a proton. So you go through beta decay twice until you get to uranium-234. And then you go through alpha decay again, and then alpha decay again. So this is one of the possible paths that a particle can take to become stable. It starts out at uranium-238, it decays to thorium, decays back up to uranium, then decays down to thorium, radium, radon, polonium, lead. But this particular type of lead is radioactive, so it decays, and then it goes back to lead. It's also radioactive. It decays again, and then it decays to lead-206, which is not radioactive. And this is not the only path a particle can take. This just happens to be the most common path that a particle takes when it's going from uranium to lead. There are other paths that you can take that would take you to into different places on this little chart of proton number and mass number. And this is what we call a nuclide table. This shows you all the different types of nuclides or isotopes of different nucleuses that you would go through as you decay through your decay series. Now the total table of the nuclides, there's actually an entire table for all the different possible decays, and it's called the table of the nuclides, and this is what it looks like. It has so this is the full version of it here. It has I need to get a better version of that. Here we go. Let's look at this one. There we go. So this has all of the, this one is actually the opposite of the previous one. It has protons here and total number down here, but it's the same idea. Actually, this one has protons and neutrons to make it easier. But the idea is still the same, where you down the center of this table here, you essentially have all these black squares are all your stable nuclides, or all your stable atoms, the atoms that can be stable for each particular element. All the other ones go through different kinds of decay by the color process. So the beta positive or the positron decays are the orange ones. These ones all go through positron decay. These ones all go through beta decay or negative or electron decay. These ones go through alpha decay up here. So you can see it's mostly in the upper part of the table, or the higher numbers of protons that undergo alpha decay. Then we have internal transitions that are these dark green ones. So internal transitions, I'm not even seeing where they are. They're kind of, I don't even know where they are, but anyway, they're hiding somewhere. Then we have things that undergo spontaneous fission. In other words, things that will just become just become two other atoms. They'll just break apart. And those are all up here in the upper part of the table as well. Things that undergo proton decay and neutron decay are these reds and these purples. And then stables, of course, are the blacks, and then some of them we don't know. And so these are all the things that have been recorded. And anywhere that you can, anywhere that you start up here, if you start up here in the orange, you know that it's gonna go through some beta decay, and so you can go down through here. And some of them, this is just the most likely stuff that might happen. And this is used to kind of track what can happen with all kinds of different radioactive decays. Now, here's their version of it again, a little more simple. Running out of time here. We're out of time, actually. Let's see here. I guess we're going to have to go another day to finish the homework. That's too bad. That's okay, though. So let's actually come back to this on Wednesday, and we'll finish up the homework. Go ahead and get started on the homework. Don't wait for me. There are some things that we need to talk about when it comes to what makes these stable, the things that what makes different nucleides stable, and also calculating half-life and understanding half-life. We want to understand that for the homework, but go ahead and try things out that you think you understand from what we've learned so far, and then we will come back to the homework next time. We will definitely finish next time, and maybe even start the next chapter next time. So we will see you on Wednesday.
See you then.
Have a great day.